See, so long as AI was a toy, which is a laboratory toy, it made no difference. But now if AI is ruling people's lives, deciding, which resumes to shortlist or which loans to be sanctioned. So ultimately computing, I would say, is about systematic and efficient problem solving. Transcends the use of computers. We cannot escape maths in today's society. I mean, everything that we do is governed by a lot of numerical facts and decisions. One of the difficulties of mathematics as a subject is that it is cumulative, right? So if you don't understand what is happening in class 5, you are not going to understand what's happening in class 6, and you rapidly fall off the cliff.
Namaskar and welcome to another edition of the Professor Mahesh Podcast, your resource to help you make informed career decisions. This podcast is brought to you by IITM Global, an initiative of the Office of Global Engagement at IIT Madras, designed to help take everything IIT Madras and India broadly to the global audience. Our research, our teaching, our startups, our enterprise, our thinking broadly. This podcast is to help you all make informed career decisions. In the episode today, we have Professor Madhavan Mukund, the director of the Chennai Mathematical Institute, a theoretical computer scientist by training, and someone who works very closely with some of the best mathematicians in India today. Thank you for choosing to come on this episode, Madhavan. Thank you.
Thank you for the invitation, Mahesh. It's a pleasure to be here.
Let's start a little bit with your own academic journey. You started first at IIT Bombay, and you obtained a BTech Computer Science, and then went to do a PhD at Aarhus. Tell us a little bit about computer science in 1982-86 in India of that time. What was it like to do computer science during those days?
Yes, it was computer science itself, of course, was a very young subject. And in particular in India, I think computer science programs were just starting. And there were, I think, at least in IIT Bombay, I think computer science was seen more as an extension of electronics. As a kind of the computational machinery. Not so much, I would say, about, the mathematical underpinnings or even software, even though there were very strong groups in software. For instance, IIT Bombay had very antiquated computing equipment, but IIT Bombay produced an excellent Fortran compiler which ran on this very resource constrained machine and made it possible for us to actually write and run programs in the 1980s when it was difficult. But there was very much a perception at that time that a lot of the interesting things in computer science were to do with VLSI, building chips, building circuits, and so on. And not so much emphasis, I would say, on, software as a whole, but certainly not so much on theory. So from that background to come to theory was a little bit of a switch for me. When I graduated, I think I did not have any intention of working in theory. I was quite comfortable with the idea of building systems, software systems. So I did a BTech project on a compiler. And then I started working for what was called NCST in those days. It's now a part of CDAC in Bombay, the National Center for Software Technology. And this had been incubated inside TIFR. So it was designed at that time or intended as a software development resource for public service, so for government and for PSUs and so on. And they had just moved out of TIFR and they had started doing some kind of R&D, applied R&D work. But it so happened that they still had hostel space in TIFR. So my initial 6 months was spent staying in TIFR and commuting to work. And in TIFR, I came into close contact with the computer science PhD students who were working largely in theoretical computer science. And I got fascinated by the kinds of discussions they were having with each other and the kind of ideas that were being thrown around and how they were part and parcel of computing, even though I had not appreciated it probably as a BTech student. So that got me into this, and they persuaded me, in fact, to trade my job for a PhD.
Oh, wonderful. Many don't know, but in the late 60s and 70s, TIFR was a world powerhouse in computer science. They had one of the world's most powerful computers, thanks to the vision of Dr. Homi Bhabha and a few others. Computer science in India was just taking shape, even at IIT Kanpur, IIT Madras, IIT Bombay. What was the industry like around at that time? Did you get a feel for it as a student?
So as a student, I must say that we were not very aware. Of course, I think TCS had just about started, and I think maybe the consulting industry was just in its infancy. And of course, there were a few tie-ups with because personal computers were just beginning to come in, or not personal, but maybe business computers, but of not computers which filled a room, but which could be placed inside an office. And so there were some hardware tie-ups, Tata Burrows and so on. But I think that honestly, I don't think that we really had a very clear idea. But it didn't look like for us at that time that industry in India was a very worthwhile opportunity to pursue after BTech. And so either one would look for these kind of at the government was making initiatives. So soon after this, we graduated. C dot started, for example, in telecom, which was also interesting from a computer science perspective to some people. But then places like NCST were probably more attractive, and maybe BARC and places like that which had some applied computing. But I think the vast majority in those days were thinking in terms of higher studies, going for masters, and then looking for jobs abroad if necessary, but not so much in Indian industry.
So, from your days at TIFR, what was your professional career? Where did your professional career take you after that?
So actually, though I got my degree from Aarhus, it's actually my PhD is more from Chennai than from Aarhus. So at that time, in the mid 80s, was when the Institute of Mathematical Sciences, IMSC here, underwent a kind of transformation and a new growth period. So Professor Seshadri from TIFR came as the head of the mathematics group, and he was quite receptive to the idea of theoretical computer science being a part of the mathematics research thing. And so Professor P.S. Tyagarajan, one of the more well-known Indian theoretical computer scientists, was migrating back from a long stint abroad. And so he came to Chennai and set up a group which is now basically the nucleus of what is now both, I would say, the computer science group at Institute of Mathematical Sciences and at CMI. When I was in TIFR, one of the people there was coming to join IMSC as a faculty member. And so he persuaded me to write to Tyagarajan, and I wrote to him and he invited me, and he immediately said, please join. And that's how I became a PhD student in computer science. So I was here for about 2.5 years, and then by some circumstances of the time, a part of the group led by Seshadri and Tyagarajan left IMSC to start a new institute, and that is what became eventually CMI. But as luck would have it, because of my background and because IMSC and CMI in those days had an affiliation with Madras University, Madras University would not let me register for a PhD with a BTech.
Okay.
So, because of these peculiar circumstances and the fact that Tyagarajan, before coming to Chennai, had been in Aarhus, he spoke to some of his former colleagues. And in Europe, in many European universities, including in Denmark and Netherlands, they have a form of the PhD where you can take published work and string it together with a kind of over some introduction and put together a thesis which is made up of publications. So that is the reason why my degree is from Aarhus, even though I spent less than a year actually in Aarhus. But I spent many months after that visiting Aarhus. But really, it's a Chennai PhD disguised as an.
Wonderful. I think there are, I don't know how many institutions even today would take a BTech student into their PhD program in India today. So, and then, so that's mathematics and Chennai seem to have been inseparable for a long time. IMSC has played a central role. IIT Madras has supported that effort. And CMI, tell us a little bit about this very unique institution, its origins, and where it stands today.
Yeah, so CMI, as I said, started with this kind of maverick move. So I think the origins of CMI, of course, there are some other reasons why Seshadri wanted to possibly move out of IMSC, but one of the main things that I think he had in mind at that time was to start some kind of teaching program to support, because IMSC is like TIFR and many other such institutions in India are purely research institutions. They only take PhD students. And this has been, unfortunately, a historical trend which has possibly separated out the research groups from the teaching universities in India. And Seshadri wanted to bring that connection back. And unfortunately, the mandate of such institutions, especially in a government setup, is very hard to change, because you need certain, fundamental things to be done to be able to do this. So part of the motivation for moving out was to eventually have a teaching program, and it took a long time. But even more experimental was that this new institute was set up under private funding.
Yes.
So initially it was under the SPIC Corporation for about 10 years. And towards the end of, 89 is when it started, and 98 finally an avenue opened up for starting a teaching program. As you, like my PhD, the main bottleneck was who will give the degree. So we found a very supportive person in Professor Dikshit, who was a mathematician himself, but who was the vice chancellor of the Open University in Madhya Pradesh. So he was able to pilot this through their system and make CMI degree come through them, but give us full autonomy to run the program. So with a very small beginning, we started the teaching program. And that, I think, has been the differentiator between CMI and some of the other institutions, in that, a research community of mathematicians interacting with a small group of students on a kind of peer basis. And that has made, I think, all the difference in how the institute is shaped. And of course, it has grown a lot since then. In those days, it was really tiny. And we had, less than 10 faculty and probably a handful of even undergraduate students. The batch sizes were 10 and so on. But it was a very, I think, good nucleus to build from.
I think people like Professor Sheshadri, who sort of started with a mission, have really, this handful of people have made a difference to the country in many, many different small and big ways. Let's step away from the institutions and talk about math and math in India today. I think there's a recent study that I came across that progress in math and performance in math by students largely is one of the earliest indicators of increasing GDP. It's not just a positive correlation, but almost a causation. India is at the grassroots level, there is a complete adoption of the idea that math is a wonderful subject to study. Nobody would argue about it. You'll occasionally hear a few things, a few people say, math is not for me. That's perfectly all right. But across the board, there is this idea that math is a wonderful subject to study in India broadly. So we seem to be in a good position. Tell us, from your vantage point, where do you see school math vis-a-vis the global level? Where is India good? What is India good at, and what could India adopt and change and improve?
As you said, the culture of studying mathematics, I think, is deeply ingrained. Fortunately, people see value in mathematics as a subject, and it's sort of equated with doing well in life. Right? So somehow if you do well in mathematics, then you're good. But unfortunately, the flip side is also that if you don't do well in maths, you're perceived as somehow not having the capability to do anything worthwhile. And that, I think, is not a good way of putting it, because one of the difficulties of mathematics as a subject is that it is cumulative, right? So if you don't understand what is happening in class 5, you are not going to understand what's happening in class 6, and you rapidly fall off the cliff in terms of keeping up with the class. So I think where we have possibly not done a good job is to have multiple pathways through the school system to keep students engaged at different levels of ability, comfort, and interest. So ultimately, if students are doing it not out of interest but because they are compelled to, and then it becomes a mechanical learning some rules and applying some procedures and not understanding why the answer, not even being able to check if the answer that they have come up with makes sense, they are not really achieving much in terms of other than teaching people some, and also a lot of emphasis on precision, getting the right answer rather than understanding why you reach that point. So I think we have a long way to go in terms of possibly scaling up the math teaching pedagogy to account for the differences in general. I think I don't have any doubt, looking at my own children, that different people have different aptitudes for maths. For some people, maths comes naturally. For some people, it is a struggle, and it is a reality. I don't think we can shy away from this. But we should not reach a situation where those who perceive maths as being difficult are kind of dissociated from math, because that leads to a problem in terms of engaging with society as large, because we cannot escape maths in today's society. I mean, everything that we do is governed by a lot of numerical facts and decisions, like even deciding which mobile plan to opt for. You need to have some quantitative reasoning skills to just cope with our modern day life. So I think that is the gap that we have to bridge. And it's a tough call, because there are lots of pressures, including the fact that school teachers have to be kind of equipped with the necessary material, not just the teaching skill, but they need to have support material, because they are very stressed in terms of the number of students they have to handle. So we need to provide enough support so that they can deal with different types of students. And the curriculum, I think, should be a little bit more flexible. Now, that is also a challenge, because then you need that many more types of teachers to teach. So overall, I think it's a human resource problem in terms of, I think, implementing the ideas that would be ideally required. But the fact that we have, I think, a cultural, adoption. And one of the things, I think, which we find less in India, I would say, at least at school level, than in other countries, there is this perception in many countries that girls are discouraged from doing maths. Now, if you look at school performance in maths in India, I don't think really there is any difference up to school board levels of girls and boys. So I think at least we have avoided...
Actually, girls outperform boys.
Yeah, so at least at school level, we have avoided this kind of genderization of maths. But unfortunately, after that, there are other factors which come in with competitive exams and all that, which I think are biased in different ways. But I think at least we have done some things right. But I think there are a lot of things I think we need to do, because the system of education has, going from a system where students studied in small, not everybody studied up to high school, and not everybody studied in all subjects, to a system where you have a kind of universal expectation that everybody studies these subjects. You have to adapt to the fact that once you make it a broad spectrum program, you also have to cater to the spectrum of students who come through that program. So that's something where I think we need to work, and we are trying to work. I'm also involved with the NCRT in redesigning the school textbooks for maths, but it's a hard sell, mainly because of this whole thing, this linkage to the training teachers and making the resources available and everything.
I remember when I was in 8th grade, and this is now 84, 85. I remember there was a choice that students could make between choosing to do what was at that time called general math versus composite math. Composite math had more algebra, more next advanced geometry. The general math was more simple interest, compound interest calculation, a very utilitarian view of mathematics. I thought there was some merit to that approach, and students chose where they went into. Is that what NCRT is coming back to?
So that is, to an extent, a little bit like that. But I think now there are even broader, beyond just the kind of subjects which traditionally would go in what we would call maybe business math, as you would call it. But now, for instance, there are a lot of interesting ideas that every student needs to know about, just as we were talking about numbers, right? Every day you read the newspaper, there will be some chart or the other, quantifying some aspect of life. It might be talking about sale of bicycles, or it might be talking about heat, temperature in summer temperatures. So if you can't understand data, if you cannot, analyze visual graphics, you cannot make sense of charts. So these kinds of skills also, I think, and these are used also from a subject perspective across the board. Social scientists, life scientists, they need to know these kind of things, because there is a lot of math modeling which goes in these subjects. And if you turn them off by making all mathematics only about calculus and engineering, then you are doing a great disservice to the community as a whole. So I agree that, we have to have these kind of things, but there are a lot of other pressures, because as I said, the school system has to adopt both kinds, has to have teachers for both kinds. And there is also, of course, this vexing issue which is behind the thing about how many students are failing in maths. Because ultimately, if you make maths challenging, students are not going to do well, because it is a problem-solving subject, and not every problem immediately strikes you as a thing that you know how to solve. So if you want to make everybody pass in maths, the tendency is to make everybody take the lowest level of mathematics. So if you have two choices, one of the criticisms is that schools will opt to offer only the less challenging choice, and therefore you will do a disservice to the students who need strong. So there are many issues involved, but broadly, yes, I think that up to a certain level, say up to 10th grade, everybody should study maths to a level where it is applicable to whatever interests they have. And maybe in class 11, 12, when they are specializing, you could have two streams. One which is more towards what we now have, which is the science and engineering kind of math, and one which is more supporting through statistics, probability, and other aspects, people who would use it on a day-to-day basis in whatever discipline they are following.
So that's a good perspective on school education. I think let's switch and talk about college education. We have BSc math programs, then we have MSc programs. As per the All India Survey on Higher Education, today in India, we have about 26,000 MSc graduates coming out annually, and about 300 plus. This is only mathematics, not theoretical computer science. 300 plus PhDs coming out. What is the college math education system like in India today? I know CMI is the crown jewel of math education in India. What is the rest of the education looking like? What are some things we can learn from others outside for that the system?
So I think, unfortunately, from what I hear, so if you leave aside some of these institutions which are kind of operating at a slightly different level. So CMI is, of course, purely math, but even if you look at IITs or the ISERs, the Indian Institutes of Science, Education and Research. So there are a handful of these institutions, which are kind of offering attractive math, but even they struggle to get, for example, an ISER has, say, 200 students joining across 4 disciplines, say physics, maths, chemistry, biology, and maths. Typically, my guess is out of 200, maybe 10 or 15 will be opting for maths. So it is a low volume of students who are taking up maths, even in these big institutions. So CMI, of course, is by nature a small institution. We take about 40 to 50 a year. But Indian Statistical Institute has a BMath program. They also take about 50, 60 a year. So the number of students actually opting for doing mathematics in these so-called, tier 1 institutions is still in a few hundreds, I would say, overall, if you add it all up. If you switch to the traditional, the classical college things, there the BSc Maths thing seems to fluctuate a lot. And what I've heard from people in the last couple of years post-COVID is that the uptake is really poor. So many smaller colleges, see, every college has to run a maths department simply because there are maths courses which are being offered across disciplines. So you cannot shut down a math department. But there are not enough takers for a BSc or an MSc in maths. MSc is, I think, even more rare. So there are many colleges which are actually closing down sections or closing down their BSc program completely due to lack of takers. It's a very bad sign. And perhaps the reason for this is also related to the perception that people have that the kind of BSc Maths curriculum that they are studying, maybe if they feel it is not somehow relevant to professional careers afterwards. I'm not sure exactly what are the reasons for this, but somehow there seems to be a lack of social value attached to this. People would rather do something which is more like a BCom or something like that, or even a BSc in pure sciences. I don't know whether the situation is similar, but there seems to be a particularly negative view maybe among people who put their children in college of what a BSc Maths has to offer. And I think we need to change that perception to get more, because the numbers are not really a good indicator. Really, the question is whether the students coming out of these programs are properly trained in the subject and how many of them are actually inclined to follow up and do something more related to what they have studied. That is really a better metric. And I'm pretty sure when you say 26,000 people are coming out of masters in mathematics, I'm pretty sure that only a few hundred are doing anything related to mathematics after that. Many of them are probably looking for some run-of-the-mill career which doesn't even require the skills that they have.
So what would be some careers, even globally, where you would be convinced that that person is still doing math as a career?
Yeah. So this is a difficult question to ask. Of course, traditionally there have always been in the engineering and design kind of careers where you obviously need. I mean, even fields like architecture and so on. I guess but civil I mean, any kind of engineering related career, there will be roles for people who have mathematical modeling skills and all that. But of course, increasingly we see for the last several decades that finance has become a very mathematical activity. I mean, we have all these very complicated. I mean, of course, one part of it is just economic modeling, forecasting what are the trends, and deciding whether interest rates are going to go up or down and where to invest. But even the kind of instruments, as they call them, which one can invest in, you have these futures and these kind of options and all these kind of things. I mean, designing them, what is the correct reward to be attached to one of these instruments. These are all very mathematical activities. And I think a lot of the finance companies are looking for people with that kind of mathematics training. It's not necessary that the person knows anything about finance or the world of these options before they join, but they should have the mathematical skills to appreciate what kind of models are being used, and of course adapt them, because this mathematical modeling in a context like economics or finance has a very different role from mathematical modeling in, say, in physics or biology. See, if I have a wrong model of gravity, it will be wrong. I mean, there is a reality of gravity and there is my model. So gravity is not going to change because I've posited a wrong model. But when you have a wrong model of economic behavior and people follow it, then the behavior of people changes, and then your model itself influences somehow how. And even if you have the right model, if the model assumes that minority of people are doing something intelligent, and if the majority start doing the same thing, then it is no longer a. So these are very tricky things, So mathematical modeling in these kind of areas requires constant adjustment. So it really requires somebody who has a good feel for how to use the tools and the techniques. So this is definitely one area. But in the last, I think the biggest domain, which is now cross-cutting in the last 7-8 years, is this explosion of data. Everybody has data and they don't know how to make sense of it. Right? Because everybody has computational devices. Everybody has, even manufacturing factories have these instruments which give out health information about their various shop floor, right? So if you can tap into this, you can make a lot of decisions. Of course, retail, you don't even have to ask, because if they know customer profiles and buying habits, they can, of course, inventory and sales targeting. So I think across the domain, and entertainment is one of the big things. Netflix made a lot of its headway because of being able to predict customer preferences and so on. So whether it's entertainment or retail or manufacturing, or again companies like pharma and so on, there's a lot of mathematical modeling which goes into different kinds of data depending on the nature of the thing. So I think that is probably, to me today, the largest domain in which people with mathematical skills can make headway. But I think finance remains attractive because usually it pays higher. So,
You just explained, in fact, the power that mathematics has on our lives. It's all pervasive. It's all around us. I can be the expert at predicting the sunrise and go to my king and say, sun rises in the east. But today's king will ask me, bring me some data and proof to go with it. Right. So, in some sense, what you're suggesting is it's mathematics training, formal training towards a bachelor's, master's is good, but develop the skills required to apply it to a different discipline while you are in college. For example, I'm just paraphrasing or sort of adding on to what you said. If an MSc student also gained some footing in the finance world, that person would be far more employable. How could somebody do this? Are there online resources, or what would be a way to do it?
Resources, of course. Now the great thing about today's world is that resources are in plenty. The difficulty is in understanding which ones to follow, because there are almost too many. It's like giving somebody a library and saying, go and read through it, right? But as you said, I think there are core skills and there are, of course, domain specific skills. So core skills, I would say that now, for example, some facility with programming or doing, because we have gone beyond the stage where we can do all this kind of mathematical analysis by hand. So one has to have a little bit of comfort at least exposure and willingness to work with. And tools are now it's no longer the old days when you have to start writing code by, punch cards and all that. There are lots of tools and lots of things which make it quite easy to use, but one has to be not afraid and have some basic computational skills. And the other part of it is that, try to understand a little bit about different domains. As I said, I don't think that most companies are still demanding that they get people who are well trained in that particular domain, because I think they're willing to give them that training, but they have to be receptive to that training. And that is where I think they're really looking for that thinking capacity. And above all, I think this is what a degree in mathematics teaches you. I think it teaches you a certain style of thinking. And I think that is not, it's not a simple thing to absorb.
No, I think, math training, you've taught this course in our BS program on something that I'm right, computational thinking, right? And these are skills that a mathematician naturally imbibes into them. And these are skills that are absolutely important for, becoming a successful applicational computer scientist at some point. Let's switch and talk about research, original knowledge being produced in India. That's at a completely different level globally today. And where is India at? And what do you see as the steps that we need to take to really be globally competitive there?
So I think, as in many of the disciplines, not just in mathematics, I think we have a few very strong centers which are competing internationally in the level of mathematics and related subjects that is done in India, but probably too few. So I think that given of course, this is always a dangerous thing to say with respect to India, because India is so large. So if you divide by the denominator of India, everything is microscopic. But I think given the scale of India, I think there should be more such centers, because also mathematics has gone from the last couple of 100 years, has gone from being something where, an individual can really work in isolation and make headway. It is a community effort, because the nature of knowledge has become so diverse and so deep that it's very hard for any one person to understand all the kind of connections and ramifications that may be needed to solve really abstract problems in mathematics. So we lack that. Is where I think we are not doing so well, which is to have these large enough groups of people talking to each other. So the research community in India, and I'm saying this is not only for mathematics, it is a general comment, it is a little fragmented, because each institution that we talked about, all the, TIFRs or IISc or IIT, or each of them, of course, has a very strong department on its own. But each such department would be small compared to a corresponding, say, department in a large university, say in a place like the US. And in that department, there will be a few people working in different aspects of it. And there is not much interinstitutional research collaboration, unfortunately, in India for various reasons. But part of it is just logistics. Until now, when now it is possible to move around and to meet online, it just used to be very problematic to have collaborations across cities and so on. So I think that is something we need to try, and maybe we could now, because we have, of course, very much better communication networks, and we should have maybe more places or interaction points where people come together and talk to each other about related things that they are doing. But India has produced, I think, a lot of very strong mathematicians. Some of them, of course, have ended up moving out of India also to pursue their research. But given our constraints, I think we could do better, but it requires a kind of collective effort on the part of the institutions involved to understand that this is in their collective benefit to actually collaborate at a research level. Because at research level, mathematics is a very different game from the kind of things we were talking about earlier when you're applying problems to day-to-day things. So it really requires a very deep understanding of very abstract things. And as I said, the subjects have become so intricate that it takes a really long time for anybody to even understand enough to make progress. So pushing the boundaries of mathematics requires a lot of groundwork in terms of training.
And the depth at which some of the unsolved problems reside are, truly require a young man or woman to spend a significant part of their life to get to the problem itself. I think that's become the nature of.
Yeah, and some of these problems are not very, I mean, the problems themselves are innocuous looking.
Yes.
Especially, I mean, the most accessible ones for the general public are problems about numbers, many
Number
problems
theory.
about prime numbers and all that. But even otherwise, some of these problems are not difficult to explain. What is the problem? But the how to solve it in an adequate, mathematically adequate manner is requires a lot of entire branches of mathematics. So like this famous problem of Fermat of x to the n plus y to the n equal to z to the n. I mean, that has apparently only to do with numbers, but it has led to enormous advances in mathematics just in order to build the tools required to solve the problem. So mathematics has this tendency to create structures which arise seemingly unconnected to what you're trying to solve. And so many times you use techniques from one area to solve problems in another area. And I think that kind of interconnection and that kind of interplay requires, I think, people with different backgrounds within mathematics to talk to each other more. And that's where I think we need to have more conversations in the research community.
I think the sense of discovery that comes with proving a theorem like Fermat's last or others. It almost gives you the feeling of having discovered some sort of a truth that was always there, and we were the first to find it. Let's talk a little bit about, at the highest level, about the different branches. You talked of number theory. At the highest level, what are the different branches of mathematics that are being pursued in the research community today?
So, of course, there are the traditional words that we hear a lot, like algebra and geometry and so on. So algebra essentially started with, you know, manipulating symbols and so on. But the main connection is that, from the idea that you can write an equation and it can represent a physical object, like you can write an equation and it represents a line or a circle or a more complicated three-dimensional. So the connection between algebra and geometry has become an integral part of understanding how, because finally many things in a physical manifestation are actually, can imagine them to be geometric, right? So even if we look at data, for instance, right? So we are used to the idea in school that we write x comma y as a point, so it is a two-dimensional thing. But now if I give you a table which has 10 columns, even though I cannot draw it, I can imagine that it's a 10-dimension, each row in the table is a 10-dimensional point in some very abstract sense. So all the kind of manipulations that you are doing in terms of separating out which ones are similar, which ones are different, are the same as taking a bunch of points drawn on a piece of paper and drawing a line separating them. So geometric interpretations are very intrinsic to understanding, but the manipulations often involve a lot of algebra, and so there's a lot of interplay. And then there are, of course, subjects like topology, which tries to go beyond the concrete. Geometry is a bit concrete in some sense about specific curves and surfaces. Topology is more about the abstract properties, about shapes. Is this connected? It's not connected, so on. So the famous thing that to a topologist, a coffee cup is the same as a medu vada because they are both things which have one hole in them, and so on. So these are all, of course, still and different types of geometry have evolved in the last 150 years. We are used to a geometry which we perceive as on a flat surface. But if you look at the geometry on the Earth's surface, if you look at a flight path, for example, on an Earth's surface, and if you compare it to a straight line you draw on a map, like if you take two cities across the globe, say you want to fly from Chennai to Frankfurt or something like that, and you draw a straight line on a map which you think is the shortest path to fly, it is actually not the shortest path because actually it's a curved surface. So if you portray it it becomes a kind of a curved line. So now, if curved surfaces have different properties from flat surfaces. For example, triangles don't behave like they do. You can have triangles which have two right angles or three right angles in a curved surface. So, but these geometries, for example, became part of, say, Einstein's theory of relativity. So space time in an abstract sense. Is it curved or is it flat? So they have ramifications in understanding, our fundamental ideas about physics and all that. And of course, even in biology now, a lot of the functioning of molecules, proteins, depends on how they fold. So understanding the geometry of those things. So geometry itself has a lot of manifestations. And so these are basically, I would say, algebra, number theory, geometry, topology broadly cover the kinds of topics, but within them there are a lot of subspecializations that people are interested in.
Very nice. Let's talk about your own discipline. What are the origins of theoretical computer science out of mathematics? How did it originate? And what does a theoretical computer scientist work on?
So first of all, I think historically theoretical computer science precedes computer science, because the first idea about computational devices came out of theory. So about more than 100 years ago, some questions were asked about the nature of proving things. So when you write a proof, if you have done kind of geometry proofs in school, you start with some axiom and you say, because of this, this follows, because of this follows. So in a sense, if you know which rule to follow, then the fact you're trying to prove becomes a mechanical process in some sense of assembling the right steps so that you reach the target that you need. So the question abstractly was that, is every statement, a logical statement about mathematics, provable in such a way? Is there a kind of automatic way where you can actually churn out a proof? And this required you to understand what does it mean to have an what is this process, right? The process of mechanical computation. How do you characterize it? And this led to the idea of what could be a computing device. And this is what we attribute to famous people like Alan Turing and Alonzo Church, roughly about 90 years ago, mid-30s, early 30s. They came up with these ideas about what constitutes a kind of mechanical computation. And the surprising thing that they showed is that there are problems which you can state quite naturally, including the original problem about all statements in a kind of logical language, which cannot be computed. So that is the most surprising thing that we came up with, that there are many things that which you would like to compute, which we cannot compute. But out of Turing's model of computation, a kind of a mathematical model of computation, came what is essentially the architecture of the computer that we use today. So the idea today is that we have this memory and we have this instructions, and then they execute the instructions. But the instructions also sit in the memory. So there is no distinction between where your program is stored in your computer and where your data is stored. It's only one place. This is all actually a physical manifestation of the theoretical computer science ideas of Turing in particular about how computation works. But more recently, after maybe 1960s, people started looking at other aspects. And in particular, one of the questions was efficiency. So you not only do you want to do things automatically, but how fast can you do them? Can you do things? So one thing is, if I can demonstrate that something is fast, I can try to explain how fast it is. But are there problems which you cannot do fast? Like, are there problems which intrinsically require you to look at a large number of possibilities? And there are many such problems which historically have been there, like scheduling. If you want to find or resource, related to that, resource allocation. So if you are, for example, an airline and you have crew and you have to fly them all over the place and they have to take shifts, how do you best allocate your staff to your aircraft so that you minimize the amount of unnecessary time that people are flying around and so on? So these are all, you could do it by trial and error. And now the question is, can you do better, right? Similar problem could be that if you're shifting your house and then you have to put all your furniture in a truck, and you want to figure out whether it will fit in one truckload or you need 2 truckloads. So what is the minimum number of truckloads, given that you cannot take your bed apart into small pieces? Right? So you have to put in as a whole. So these are all problems which are of practical importance, and computationally it's not clear that there are good solutions to this. So this idea of algorithms, efficiency, complexity, this has been one of the driving questions in the last 50, 60 years. And it has become now old enough that it's become a kind of classical problem in computer science itself, to understand this interplay between the resources that you have and the problems that you can solve. And the other part which is my research interest is that now you build more and more complicated computing systems. You need to validate that they are doing what they are supposed to be doing. So you come into this. So this is one of the original problems that Turing showed cannot be done. You cannot take a program and write another program which will check that it's correct. So you want to ask, you have written, so you're a teacher, a student submits a program. You want to know whether that program will work correctly on the, so you say they have written a program to calculate factorial or something like that. In general, you cannot tell whether it will work right across all programs. So now, but if I build a system, I will need to validate it. So how would you validate, given that there is this bottleneck, how do you do this? So it's like an engineering extension, but the engineering objects are not physical objects, but software objects. So I set up a telecom network, or I set up an automated signaling system, or I set up something which is, for example, of current relevance today, which is for software which is flying a plane. How do I make sure that it is doing the right thing? Right? So that is one aspect of theoretical computer science.
These are all, ideas in mathematics, but very grounded in real opportunities for adding value to society. And at the foundation of all this is this discipline of discrete mathematics. Tell us a little bit about what is discrete mathematics and what does it teach the student?
Yeah, so the discrete mathematics, the idea of discrete in this comes from the fact that traditionally mathematics has talked about, functions, right? So you have real numbers, and real numbers, as we know, there is no gap, right? Between any two real numbers, there's another real number. So you're talking about something that varies as you increase time, what happens to the distance, or as you increase some supply, what happens to the demand. So these are continuous things. So because the supply increases continuously or population increases continuously. Discrete is talking about separate objects. So now I'm asking you, if I have some 25 teachers, and if I have 17 courses, and how many different ways can I allocate them, right? So you're talking about problems like this, which involve separate items. They are not continuous, but some kind of orderings, reorderings, matching, and all that. So this is where the idea of discrete mathematics comes. A lot of computational problems are naturally discrete in nature, because they are, like we were talking about packing furniture in a truck. You have some finite number of objects in your house, right? It's not that you have 1.3 beds or something like that. So discrete mathematics and understanding how, it sounds very childish, but understanding how to count, right? How many different ways can you do this? So that's really counting in a different sense, not just counting 1, 2, 3, 4, but enumerating systematically all different arrangements and making sure you have not missed out anything. At the same time, you have not duplicated anything. So starting from there, so enumerating, counting properly, making sure that, or even counting the same thing in two different ways to make sure that you've not made a mistake. Then you have these ideas of graphs. So graphs are objects where you take these, so you take people, for instance, and you connect them if they are friends. So people ask these questions about social networks, for instance, right? So if you have a social network where people are talking to each other, they are somehow communicating, then how far apart are any two random people, right? Will they find one person that they know in common? Will it take two hops, right? So these are questions where you're looking at the social network graph, where the graph, you have these people and they're connected by a link. So how many links does it take to go from here to there? So these graphs have a very important role to play. So there are lots of abstract problems which you can formulate on graphs, which when applied concretely give you a lot of practical answers. So this is a slightly different style of mathematics from the traditional mathematics where you're talking about sine, cos, and or x to the 5 and so on. So that's why people sort of, I think, disconnect it in some sense from mathematics as a whole and call it a separate thing. But I think it's as intuitive and possibly more intuitive for, at least for school level students to appreciate. And it definitely gives you a much stronger grounding when you get to computing. So I think both are important. It's not that one is less or more important than the other, but this is of course more relevant, I would say, for people who are studying computing as a subject.
So let's now talk about math and computing. We've looked at the underpinnings of where math helps computer science. Clearly, math is positioned to provide the best foundation for a computer scientist, but it's not perceived that way. Computer science is now perceived to be this completely different discipline from mathematics. What can we do to solve or to provide the right information? What can we do to bridge this information gap?
Yeah, so I think, as you rightly said, a lot of places computer science is equated with the word computer, and I think it's an unfortunate choice of terminology possibly. Many computer scientists object to using the word computer science because they say it's not like, it's not like washing machine science.
As my colleague says, it's really more computing science.
Exactly. So computing science is one way of getting around it. In European countries, they call it informatics because it is really about manipulating information, right? Computing is a lot about manipulating information. So it's abstract. It's not about, and the process of doing it is what is important, and not the physical manifestation. So the fact of whether you're doing it on a particular computer or not. But here, in our context, a lot of the emphasis in computer science automatically translates to learning this programming language or learning that programming language or being familiar with this computing environment or that computing. So I think there is definitely a disconnect between what computing stands for and its manifestation in terms of physical computing devices. And this connection, I think we need to, or this distinction we need to make clear. Now, the fact is, of course, that if you have a stronger background in the mathematics of computing, you automatically become a better programmer because a lot of programming is about logical problem solving. So ultimately, computing, I would say, is about systematic and efficient problem solving. So it transcends the use of computers. You referred to this computational thinking course that we have in the IITM BS program. So that uses no programming at all, no computers at all. It's all about telling how to solve different types of what are actually traditional programming problems, but just systematically how to go about it. What are the kind of steps that you need to take? And this helps no matter what type of problem you're doing. So this, I think, is where one should emphasize. Now, of course, the attraction of computers and the ubiquity, now that everybody has access to computers, it's very easy to get sidetracked into the physical part of it, learning the language or writing. And of course, there is also a tangible reward which comes with, as you were talking about, proving a theorem, but it's even more tangible if you write a program that works and does what you think it is doing, right? So to show that, I did something and it produces output, it is a very real kind of tactile reward. So a lot of people get more focused on those aspects, and they lose track a little bit about the found. So the real challenge is that you start attacking a problem based on the tools you have rather than how to solve it. So it's like a carpenter or any other kind of a craftsman who starts hammering away because they have a hammer without understanding whether this is the first step to be done or something else should have been done before that, right? So you need to analyze the problem and then come up with the best solution. But often you just hammer away at it and find the first solution that works, which may or may not be the best one. And that is where I think the distinction comes between having a strong mathematics background and not having it.
So we talked of mathematics as providing the fundamental thinking mindset to solve quantitative problems, right? And finance is a field that we alluded to earlier that is ready to absorb this sort of thinking in a big way. Developed economies already have a track for a mathematician to go onto Wall Street and do their thing. I think it's a natural course of development that countries like India would also adopt this thinking increasingly. We talked of finance, but what are the other fields where we will all see mathematicians go in big numbers? Finance will obviously happen in India as well.
No, so finance is already happening. Of course, many of the finance companies which are hiring in India are possibly international companies with bases in India. But even some Indian banks, I think, are looking at these kind of things. But as I mentioned before, a larger perspective right now is really this anything to do with data. So we have all around us now, because of electronic commerce, right? We have a huge logistics network of people, warehouses, deliveries, all this. So there are lots of things that need to be optimized, right? So if you are a big merchant selling lots of goods, you're a Flipkart or an Amazon or something like that, then you need to first of all make sure that your customer will get what they get in the time that you promise them. Therefore, you have to keep the right amount of stuff and not too much, and you have to have a way of delivering it. So you have to have a network of, and then even if it comes down to food, Swiggy, Zomato, now restaurants are no longer cannot rely on how many people walk in through the door, right? They have to anticipate how many people will order online to make sure how much of different items to make. So logistics, all these things require some optimization. So optimization in different forms is required in many industries. So logistics is one large domain. As I mentioned before, even surprising things like entertainment, advertising, a lot of these things are now driven by analysis of how customers will react. So a lot of things are tailored based on data. So I don't think, our experience is that it is quite widespread. Manufacturing, as I said, is also becoming more aware of the possibilities of improving efficiencies, improving output, making. There's always been a demand for people in terms of reliability and quality control and so on. But these things are all converging now because the access to the data is much more, computational techniques to deal with them, and mathematical uh, uh, concepts to analyze come together. And I think this is where I think most people who have a strong mathematics aptitude will find something or the other which will be of interest to them, and where they can also play a very positive role.
That's a great idea. Let's put ourselves for a minute in the position of the employer in any one of the many sectors that you just described. I have an option to hire, let's say, an MSc Math, a good MSc Math graduate with all these skills you described, and a BTech Computer Science, so, or even possibly even an MTech Computer Science. If I go with hiring the MSc Math graduate, a good person, what will I get, and what will I not get by hiring the MTech Computer Science graduate, and also vice versa?
Yeah. So as I said, many of these industries are not per se technology industries, right? So I think if somebody has a BTech or an MTech in computer science, one of the things hopefully that they have learned and which they can apply is how to build and develop better computing systems, right? So if you have really something, an IT infrastructure that you need to develop, and you need to build up some kind of a software platform, then you would definitely look for somebody who comes with this kind of a skill. On the other side, if you have some adequate access to off the shelf platforms which people can use, and you are really more interested in applying insights into the information that you have collected and improving your kind of business in whatever way it can be more efficient, more profitable, whatever, then I think somebody who comes with a wider set of math skills is probably the correct person. And I think this is where we are seeing the shift, that the previously a lot of these things were together. I mean, the technology companies were offering solutions of this kind, but now the solutions are coming from, the companies asking for these are no longer necessarily technology companies. So I think that's where the need or the better fit for the math background graduates comes in.
Very nicely put. Let's talk about the flavor of the day, artificial intelligence. You've talked of data science. What are the mathematical underpinnings of today's AI world, and what can mathematics do for this whole field?
So what mathematics can do for this whole field, but it's very far from clear how to do it, is to kind of understand, of course, what is happening. So we are still at a stage now, I think we are at the stage where we were with natural science, classical science maybe 1,000 years ago, where we could see something fall, but we don't know why it is falling. So I think in the same way, I think we see these systems which are incredibly complicated, behaving in very, very unpredictable, but also very swimmingly intelligent ways based on the data they have ingested. But we really have no idea of knowing how they are going to work and how reliable they are. So I think the holy grail right now is to have a mathematical theory or some way of understanding how these systems evolve as they grow in terms of ingesting more data. But so that I would say is, of course, so a lot of mathematics goes into building these systems, and that is a very different kind of thing. But I would say that in the last, my impression at least is in the last several, maybe 5-7 years, a lot of the advances in the AI models and all that has actually come more from experimentation than from theory. In the sense that people are designing new systems based on some instinct that maybe this will help, maybe that will help. So it's a bit like taking some engine and tweaking, turn this valve, turn that valve,
Talk of engine. I'll have to interrupt you for just a minute. The steam engine was invented in the 1840s. A working model was realized, it was doing some things for people. But the laws of thermodynamics were written a clear 40, 50 years after the steam engine was working. I can see a parallel to this. Is one of my colleagues from Columbia, brought this out in a talk he gave. Um,
No, and I think that is very true. Similarly, I mean, electricity and Maxwell's equations are not, you don't need Maxwell's equations to have electricity, right? So the same way, I think AI has now reached that stage where people are, I would say, really it is still a very experimental science. That the unfortunate aspect of it is this experimentation is very expensive, right? Both in terms of the computational power involved and in terms of the amount of data which needs to be ingested to check whether the experiment works or not. And that has made this whole thing a little bit unequal. I think that outside these large corporations, which includes Googles and Amazons and Metas of the world, even academic institutions in large, well funded academic institutions in places like the US struggle to have the kind of resources to do these experiments. So, really, it's become a situation where one small group of industries is really making decisions about which directions to move, and the rest of the people are trying to catch up in some sense. But I think from a mathematical point of view, I think it is really, but it's going to be it's not easy. I think it's going to be as complicated as anything that we have done in understanding any other kind of complex theory as to why these things work. And of course, the other challenge is that we are no closer with all this AI models and all to understanding how actually our brain works, right? So neuroscience and computational AI are two very different beasts. So that is still a challenge, right? So we are not in a way we are not really capturing or even close to understanding our own thought processes. So it's not surprising that we are not able to actually get that right.
What I'm hearing you say is now is as good a time as any to be a theoretical computer scientist or a mathematician inclined to this set of problems. Um, and when we have written the laws of AI, so to say, what would that AI world look like? I'm sure it'll be less energy consuming, more orderly. What are we aspiring to do as a theoretical computer science community there?
So I think as a going back to what I said earlier, when you make complex systems, you need to when you deploy them, and that is where really the challenge comes. See, so long as AI was a toy, which is a laboratory toy, it made no difference. But now, if AI is ruling people's lives, it is making decisions about various things, innocuous decisions about what TV show to recommend to you, but also deciding, which resumes to shortlist or which loans to be sanctioned, and then at another level, how to navigate a car. You need to be clear why it is doing what it is doing and whether it's doing it right. Leave aside the other problems that we have, which is about fake news and influencing opinion manipulation, whether something which is being put out is actually real or whether it is being manipulated. So for all these things, I think we need to be able to have that clarity, right? So what is real, what is not real, what is the possible, what are the boundaries. So I think that is where we need to aim for. So a world where we understand these better is one where we can control it better. Say right now everybody's talking about regulation, but regulation is not possible unless you understand what you're regulating. And unfortunately, AI is not like something tangible like nuclear power, where you can say you cannot, store uranium, or you cannot. I mean, it's a very intangible resource. So how do you stop people from experimenting? You cannot. So at best, you can say, okay, when you deploy something in a public way, at least we can check whether it is doing what it's doing or not. That should be our. It's a very tall thing to reach, but I think we should aim for that.
So we talked of this explainability as a problem, right? And as an area where mathematicians and theoretical computer scientists have an important role to play, and in some sense give us all a sense of comfort when we are using our future AI tools. At the end of the day, if something is not explainable, I'm always wary of what it can do for in some unseen situation. The underpinnings of mathematics in India, educational system, uh, requires some rethink given the set of new problems that are on the horizon. Tell us a little bit about CMI's own model of at the undergraduate and the postgraduate level. What do you do that you think others should emulate, and what can we do then to scale this up to the rest of the country?
So part of CMI, I think, is because it is not scaled, I would say. Because so CMI started, as I said, with a very small program, and even now the program is quite small. So we have about 40 faculty and another 30 postdocs. And so if you look at post PhD people on campus, it is easily 75 to 80 at any given time. And we have 40, 50 undergraduates in a batch. So we have only 150 undergraduates interacting with 80 PhDs. So this is a very healthy ratio for people who want to explore mathematics, because the great philosophy which has always been there is that there is no barrier. So students are encouraged to come and discuss ideas or to explore new ideas. So there's a fairly free atmosphere of inquiry and research. And that's one thing we have been very fortunate. I don't think it is conscious, but it is something which has evolved. And maybe, like in all institutions, this is something which spreads within the student community, independent of whatever we may want. But there is a very strong peer respect and desire to do research. And this drives a lot of what CMI is about. The idea that you are really there to learn things. I think this has gone out of a lot of our institutions. A lot of our institutions have become pathways to kind of attractive jobs. And people forget that they have to learn something. They are more interested in how they should burnish their CVs, what kind of projects they should do, mainly with a view towards something outside the educational system. So I think that is something where, to an extent, this works well in CMI because it is small. I don't know if it would work so well if we had 500 students instead of 150, let alone 5,000 students. So how to inculcate that interest in the subject? So that is the main thing that we need. And I think there is, fortunately, as I said, there is no shortage of good material. I mean, there are enormous number of very, very well-produced videos on different subjects, very exotic subjects also in mathematics, which the interested student can consume. So this is the challenge. Now, how do you get the interested student to go to this material? Because the uninterested student, unfortunately, will not go even if the material is excellent, right? So there is no way to persuade somebody who doesn't have the interest to watch something because it is good. So we need some better way to identify, and there are lots of such students, I'm sure. I mean, in any population, there will always be a fraction of students who have interests in different areas and aptitudes in different areas. We miss a lot of them because our education kind of priorities are, and I said this is not necessarily a problem of the system, but it's a problem of maybe how our society has reacted to the system. But we have really created this professional course oriented mentality. Everybody wants to be either a doctor or a lawyer or an engineer or something which immediately leads them to a profession. And the role of acquiring knowledge has taken a backseat. And so we also face this. We have had parents tell us that they would love, our students who want to come are always interested in coming. But at the school level, especially, students don't make their choices. We have parents tell us that, we are doctors, we don't know, but our brother-in-law or our uncle has told us that after he studies maths, he can only teach tuition classes. So this is the kind of mindset, right? So we have to break that mindset, educate people. So podcasts like this help, that there are very viable careers outside academia, outside school systems for people who study these subjects, and get students who are really interested to come. So we should, unfortunately, like in every other area, the number of opportunities for good students is limited. That's an unfortunate thing. But even there, I feel we are missing out on good students even knowing about the opportunities and taking them. More are coming up. As I said, IIT, IIC, they have started good undergraduate math programs in some of these institutions. ICERs are there. So I think the number of good opportunities is growing slowly. But how many students are we losing because they are not even aware that this is what they want to do and they can do? That is something we need to somehow try and reach out. So I don't know what is the best strategy for that. Certainly, programs like this, or just conducting kind of summer schools, encouraging people. A lot of, in CMI itself, among our faculty, we have at least a handful of people who have come to maths after studying engineering. And I know other people also, some people from IIT Madras who have moved to maths after engineering. So I think this has always been the case, that students start in one thing and then they realize that. And so we should try to get students who are not aware to try it out and see if they're good.
I think education for livelihood versus education for life is a question that is only to be grappled with in advanced and developed societies. I think India, as we all get to that point, we will see more of this education for life rather than education for livelihood as the paradigm in which we make decisions. Back to the pursuit of new knowledge, which you said is central to most undergrad students at CMI. Today's, plain vanilla BSc curriculum in a college out there has very little emphasis on new knowledge pursuit. Would it be a good idea to add that? How could we do that?
Yeah, so it is a challenge, I would say, because even for CMI students, new knowledge is not necessarily new in the sense of research.
It could be new to them.
New to them, right? And that requires some awareness among the faculty. So I think what is really key to the CMI experiment is that the people who are teaching are actually actively involved in research. So they see opportunities from the questions, for example. We all have this experience that, once in a while in a class, a student asks something which really you may be able to answer immediately, but it sets off a train of thought which says, why this and why not that? So you have to have that openness, whereas a lot of the people, unfortunately, who teach in these colleges have a set routine. They will follow a set book and a set of notes, and they will not deviate from that. So there is no attempt also to explore beyond the boundaries of what has already been prescribed. So that mindset, but that comes, I think, with the baggage of having to retrain faculty to teach or to think of teaching in those ways. So it requires a lot of resetting. Maybe, as I said, if we can make resources available so that the teaching can go on as it is, but there could be some additional enriching material for students who are wanting to explore outside the thing. If we can have some collective way of doing that, maybe that would be one way to bootstrap out of this system.
Technology can probably help.
Technology is there and it can definitely help. As I said, the main thing is to make it, it's too much in some sense, right? So you have to make it accessible in a way that students can make sense of it. And that's where we need.
When we talk of technology and education, we can't not talk of the BS Programming in Data Science that IITM offers, in which you had a shaping hand. Tell us a little bit about the thinking behind that program.
So part of the main, I think, thinking behind the program is precisely this idea that there are talented students out there whom we are not reaching, right, through all our IITs and CMIs and all these institutions. So how do you get these students into the system or give them a chance to get into the system? And also at the same time make it relevant. And that's why I think the decision to make it focused on data science, because that, as we have been discussing, is one of the really tangible job oriented areas in which mathematics talent can be done. So the idea was to invert the situation from being one where you are very selective about students who join to being one where you admit students with a very generous minimum background, but then you are very particular about how they continue. Because in Indian systems, we are used to the idea that if you join a college, it is sort of the college's responsibility to finish and give you a degree. So now the situation is that and much before, in some sense, or in parallel with all the new ideas from the education policy about having multiple exit options and all that, the idea was that it's not that you make people leave, but you give them options to leave with different degrees of achievement. So everybody can choose for themselves that, this is enough, or this is something which interests me, but I'd rather do something else. And therefore, there's a kind of funnel which gradually takes a large number of students and filters out those. And the ones who finally finish the degree are relatively few, but a large number start. And I think that's probably the kind of model we need to see how we can replicate it, because this is the only way you can bring in, I think, people from a large cross section of backgrounds and give them an opportunity to see whether this makes sense for them or not. I'm not saying that everybody should study mathematics, but at least everybody who thinks they are interested should have an opportunity to find out whether these kind of subjects can make sense for them or not. And at the same time, it will be good if the people try it out, learn enough to make use of this, but then go and do something else. That is also valuable, because these are skills which are life skills now, I think.
And as you said, even though a small fraction only end up graduating with the final terminal degree, everybody gets a feel for good quality education. Everybody has experienced, good quality fountains of knowledge. This has been a wonderful conversation in the sense that we started talking about mathematics and theoretical computer science, and where groups of people trained in these sciences can really play a significant role in the decades of tomorrow in India. What would you tell parents and students who view mathematics as an academic subject? I mean, you said you're only going to be good for tuition classes, which is extremely far from the truth of even today, and certainly is going to be far from the truth a few years from now.
Yeah. So, of course, I mean, at its heart, I mean, every research mathematician is studying it out of academic curiosity and interest for ideal truth, as we discuss, proving theorems, proving abstract facts about intangible objects. But research is also only a minority outcome for people who come through this. Traditionally, as we said, the people feel that if you don't succeed in research, then you must end up teaching. But that is not the case at all. I mean, there are enormous number of industry areas, out there, where people are keen to get inputs with this kind of a background. So it's a question of mindset. So if the student has this openness to doing things in a domain which they may not be familiar with. See, this, if you study mathematics, it is not that you know anything about retail, or you know anything about pharmaceuticals, or you know something about whatever domain you're going to work with. But you have to be able to appreciate that the problems there have some abstract structure, and you need to, of course, understand in what context to apply. So it just needs a little bit of openness, and there's enough material around to study these things and understand it at a high level, at least as a student. But there's no need to. I think the companies don't expect students to have domain knowledge. They just need them to have this kind of mathematical thinking skill and problem solving. I think problem solving is the biggest challenge. That, for example, CMI students who go out into data science jobs, our feedback from the employers has been that after 2 or 3 years, the distinguishing factor from people who come from more traditional statistics programs is that as the problems change, because everything, as we said, is evolving, the nature of the problem, the nature of industry is evolving, these students are better at coping with this change, adapting themselves, because they have been trained to think in a kind of independent way about problems, rather than being trained to look at certain tools and certain solutions as the only way to do something. So I think that independent thinking skill is what really distinguishes people who study maths in this true sense and makes them capable of adapting.
If there is one discipline that we can guarantee will not go out of fashion, it is mathematics. I mean, as deep as it has gotten into our lives, and the D by DT on that, it's only going deeper and deeper into our lives. I think there are very interesting careers that are in the offing for sound mathematicians to go appreciate domains and solve problems in those domains. This has been a fascinating conversation. I learned a lot, and thank you, Madhavan, for coming.
Thank you, Mahesh. I think it's a great opportunity, and I hope that this reaches out to some students and parents and convinces them that mathematics is something they should consider as a viable option if they are really interested in the subject, and not shy away from it.
Sure. I'm certain it will. Thank you again. This is the Professor Mahesh Podcast, brought to you by IITM Global, an initiative of the Office of Global Engagement at IIT Madras. Your resource to help you make informed career decisions. Until the next episode, be well, do good, and keep in touch. Namaskar.